Hello everyone, my name is Matt Anderson and I'm here with ChemEasy to give you the second video, or walk through the second video in the series on distillation. And the topic of this video is something extremely exciting, and it is vapor pressure. I remember one of my classes, I had a professor when he was first teaching us about vapor pressure in one of my first chemical engineering classes. He asked us to go home, the assignment was go home and explain vapor pressure to a friend. Well, it's quite a few years later and I'm now hopefully explaining it to a lot of new friends. Anyways, with vapor pressure, I wanted to give three different definitions because this concept is absolutely key to understanding distillation and really most concepts in engineering. And I think that vapor pressure is a good thing for almost anyone to understand. It just gives them a good idea of how the world works around them, such as things such as evaporation are vapor pressure. And so we're going to give three definitions. I'll give three definitions. The first one being a formal-ish definition. Maybe it's not perfect, but it will suffice. So the formalist definition goes as follows. The vapor pressure, which will be written as PV, you also sometimes see it written as, I'll just put it right here, PSAT, you'll occasionally see, or a P star, possibly. So the vapor pressure is a PV of a pure substance is the pressure exerted by its vapor in phase equilibrium with its liquid at a given temperature. Kind of sounds a little crazy, but imagine that you have a cup, we'll say, of water sitting on a table. There we go. It's a great table. Now, if you have the liquid water here, some of it will actually vaporize, and we talk about this with the thermodynamic equilibrium in the last video, where we talked about the chemical potential of the liquid equaling the chemical potential of the vapor. And so if there is absolutely no water in the air, we'll say, no water vapor, then some of the liquid water will actually change phase and will vaporize so that can reach a lower chemical potential. And that's how humidity works, actually. It will be more humid. We're talking about the vapor pressure of water. Moving on, the alternate definition, if that didn't work for you, would be that given a temperature, it's the pressure at which a pure substance changes phases. So most of you know that water boils at 100 degrees Celsius, but we need to be a little bit more specific. We can say that water changes phases from a liquid to a vapor at 100 degrees Celsius at atmospheric pressure. And there's a key relationship between temperature and pressure and phases that we need to be more specific in chemical engineering. For example, if your pressure is lower, for example, if you're at a higher altitude city such as Salt Lake City or Denver, water will actually boil or change phases at a lower temperature. And this is a function of vapor pressure. And so if that didn't work for you, the alternate definition as well, maybe you're a visual learner. So for visual learners, we also included a chart which is very helpful. And what this chart is that it's the pressure and temperature plotted against each other with the phases shown as solid, liquid, and gas. So this is called a PT, so for pressure and temperature, PT chart, PT plot, and you'll see this a lot in chemical engineering. It's very useful in understanding. And each pure substance will have a different PT chart, but the general shape is about the same. So for this example, we can consider water. Now let's say we have pressure, which is atmospheric pressure, and I'll just write this as a note as well. Atmospheric pressure is going to be equal to 101.325 kilopascals. This is also equal to 14.7 psi absolute. We can also say it's equal to 760 millimeters of mercury. So any of those you can consider your atmospheric pressure. You can also say it's equal to 1 atmosphere, well, about equal to. And atmosphere is also a unit of pressure. So we'll just say right here that we have, we'll label this pressure right here being 101.325 kilopascals. So just a normal sea level, your pressure. So if you start with water, you're in a solid phase right here. Well, we know that water is ice anywhere below 0 degrees Celsius. So we'll say maybe this temperature down here, we can say negative 20 degrees Celsius. Now let's just say we heat up this water, but not change. We keep the pressure constant, isobaric. As we heat up the water, moving this way, eventually we reach this line right here. It's a very foreboding line. Now, we can consider this is where the phase transition would occur, and you can label this then point right here then as 0 degrees Celsius. If you continue to heat the water, you add heat to it, you'll eventually reach this line between liquid and gas where water vaporizes, it changes phases. So you can label this temperature right here as 100 degrees Celsius. So from our alternate definition, we can see that the vapor pressure of water at 100 degrees Celsius is 101.325 kilopascals. Now this line right here, you can consider your vapor pressure curve. Anywhere along this line, at these pressures and temperatures at this line, you will find liquid and gas in equilibrium with each other. You can find liquid and gas present at the same time. However, if you move off into any of these areas, liquid or gas, and you have a single substance, then only that substance will be present. Okay, so that was the formalish definition, an alternate definition, and for visual learners. Now we're going to do a brief application. Okay, so let's do our vapor pressure application. Let's look at this tank right here, this beautifully drawn tank, tank 501. The pressure is at 101.325 kilopascals, which you know to be atmospheric pressure, and the temperature is 57 degrees Celsius. Now the problem statement here is that the TK501 has only H2O, has only water. There is no air present inside the tank. My question is, pulling on all your knowledge of water, what phases are present inside of tank 501? So that would be solid, liquid, vapor. And you can say how many and what phases. And my hint would be to remember to look at or even draw out a PT diagram for yourself. So I'm going to pause here for a second to let you do it. Okay. Now the answer to this question of what phases are present inside of tank 501 when the pressure is at atmospheric conditions and the temperature is 57 degrees Celsius is clearly only water. There's only liquid present. Only liquid is present inside this tank. And this is because if you were to look at our PT chart below, if we say call this temperature right here 0 degrees Celsius, and maybe this is 100 degrees Celsius, and then we have atmospheric pressure right here, as you go through this region, you can only have, it's a little bit off, let's draw it up here. Okay. At these 2 points, if the pressure is at, you can have both solid and liquid present or liquid and vapor present. So if you're at 57 degrees Celsius, somewhere right in the middle, 57 degrees Celsius, then you'll be in the all liquid region. Where people get confused on this type of problem is that they associate this with, they assume that air can be present. Because clearly you can have a water bottle at atmospheric conditions that has both water, that both has liquid and vapor. However, the difference is that there is air inside of that. If you have a pure substance such as only water, then you have to go by something like a PT diagram to see at what points can the vapor and liquid be in equilibrium. Because if you don't, then there will only be one phase present, like in this example. Okay, thank you very much. And next time we're going to be covering Raoult's law, which is an exciting application where we use both equilibrium and vapor pressure in conjunction with each other. Thank you.